Right, this is another video. This is going to be section C of the June 2023 paper. Okay, we're going to be looking at electrical and electronic principles. Right, start off with multiple choice questions. So identify the electrical theory that states the algebraic sum of all voltages within a closed loop network must equal zero. Right, we're talking about circuits, we're talking about voltages. Immediately two people pop up, and that is Kirchhoff and Ohms. And fortunately, I can only see Kirchhoff here. Okay, so that's going to be my gut shot. That's going to be my gut feeling. It's going to be Kirchhoff off the bat. Okay. Right, so question 14. Identify a unit of measure for reluctance. For this one, quite frankly, I'm not too sure. However, I know how I can figure it out. I know that there is a formula in the formula booklet. Let's go find it. There we go, that page. We've got a formula for reluctance. Reluctance is just here. It says S equals Fm over that symbol, that Greek symbol there. So I'm now going to look for the calculation for Fm. Fm in magnetomotive force. Fm equals N being the number of turns of a coil, and I being the current, which would be in amps. So I'm looking for turns in amps in my units, and it's going to be A. Ampere turns per Weber. Okay, no other one has amp or turns. That is ohm terms, but not useful because we're not dealing with resistance per se. So it's going to be A, ampere turns per Weber. Okay, so we can use our formula booklets, use our formulas to help us with our units. And that is going to be the multiple choice section dealt with. Always go through a process of elimination if you don't know the answer outright, and even if you don't get it, it's only one mark. You focus majority of your attention onto the calculation questions. Right, question 15. A DC power source is connected to three capacitors in a combined series and parallel arrangement. Calculate the total capacitance of the two capacitors connected in series, C2 and C3. So we're dealing with these two over here on the right. Okay, capacitors work in the opposite fashion to resistors. Okay, so resistors, when they're in series, you just simply add them up. When they're in parallel, you add them up by 1 over resistor 1 plus 1 over resistor 2. Okay, now these are in series, therefore we're going to have to not go and just add them up straight away. We have to do the opposite of resistors, which is the 1 over. Okay, so let me write down the formula. 1 over C1, actually I'm going to put C2 because we're using C2, plus 1 over C3 equals 1 over C total. Okay, we're going for the total of the capacitance over here. So let's now substitute the numbers in. 1 over C2, which is 33 farads, that's lovely. And then plus 1 over 56. Okay, that's going to equal 1 over C total, which is the equivalent of, right, don't bother trying to do it in your head, use the calculator. Okay, fractions are quite tricky, so let's just play it safe. 1 over 33 plus 1 over 56 equals 89 divided by 1848. Right, so 89 over 1848 is equivalent to 1 over CT, but we want the value CT. Okay, to get from 1 over CT to CT, we must times by its inverse. So inverse is going to be to the power of minus 1. So I'm going to take my answer that I've got here and simply times it by to the minus 1. And that is going to be my final answer. CT equals 1848 over 89. In number form, that is going to be the number I saw on the calculator, which is 20.764, so on and so forth. Okay. And that's going to be measured in farads. I know it's in farads because over here we had these measured in farads as well. Okay, so I'm going to put 20.764. I'm going to put the capital letter F. And that is on my answer line, just at the very bottom there. Right, that's another 3 marks. So let's move on to question 16. Question 16. An engineer takes readings across the terminals of a DC electric motor. They record a supply voltage of 120 volts and a current of 5 amps. Calculate the input power of the DC motor. Give your answers in appropriate units. Right, lovely stuff. Okay, so we're looking for the input power. I am going to jump straight to my formula booklet. I might as well. I do believe that the formula will just be P equals IV. But let's have a quick look. So we're looking for input power, more specifically power, but the fact they've said input power, yeah, okay, the second question, output power, so they're looking for the efficiency equation as well in part B, hence why they put input power here. So what I'm going to do is I'm going to look for the word power. There we go. We've got power equals I times by V. Okay, that's what I'm going to use because I know that I've got an I, which is a current, and I'm going to have got a V, which is a voltage. So writing down P equals IV. I've got a voltage of, sorry, I've got a current of 5 times by a voltage of 120. Therefore, I'm going to have a power equivalent to 600 watts. Okay. So my answer is going to be 600 watts. Now, the engineer tests the DC motor and finds it to be 65% efficient. Calculate the output power of the DC motor. Right, let's have a quick look. We've got an electrical efficiency equation just here. It says efficiency equals power output over power input. Right. I've got a power input of 600 watts. I've got an efficiency, so let's write this down. Efficiency. Efficiency equals power out over power in. Power in is 600. So let's rewrite this. I've got 65% equal to P out over 600. Therefore, what I'm going to do is I'm going to times both sides by 600 to get P out. Okay, so 600 times by 65% equals P out, which is equivalent to 60% of that. That's going to be 360. Ooh, 390. Let's just double check. The equivalent of 65% as a decimal, okay, is going to be 0.65. So 0.65 times by the input, which was 600, and that's going to get me, there we go, 390, and that is watts. Okay, so 390 watts of power is our answer, and that is a total of 6 marks for that question. A very nice question for me personally. Hopefully this is as straightforward for you as well. Do remember, if you do have any questions, please just go to the comment section. Okay. Ask your questions there. Right. I'm straight away, I'm not even looking at the question properly. I'm just grabbing my formula booklet because I already know which formula I'm going to need to use. There's only one formula we can use that's so specific for this question, right? I'm just going to quickly tell you now, because I've got these two balls, all right, with a distance between them, I'm immediately jumping to this formula here. Okay, it's the Coulomb's law. Right, let's read the question now. Question 17. A maintenance engineer services powder coating equipment that works on the principle of electrostatic attraction. The charges on the two particles have been recorded. So you've got Q1, so the charge on this is 1.2 times by 10 to the minus 16 coulombs, and this one is 1.7 times by 10 to the minus 16 coulombs. Okay, very, very, very small numbers, but then again, they are particles, they're very small, so these charges relatively are quite large for them. The force between the two particles, 8.2 times by 10 to the minus 8 newtons. Okay, that, as you know, is quite a very weak force, but that's a weak force for us because we are quite large in comparison. Okay, we need to calculate the distance r between the two charged particles. Lovely stuff. Right, first of all, what I'm going to do is I'm going to write my equation out. Force equals Q1 times by Q2 all over 4 pi epsilon naught r squared. Right, we've got everything here apart from epsilon naught. Epsilon naught is a number which we can find in our formula booklet. Okay, so I'm just going to quickly find that now, and then I could show you whereabouts it is. It's like a number like gravity or permeability. Exists somewhere close to the first couple of pages. Okay, there we go. Physical constraints. It's just after the quadratic formula. It is on the 3rd page of the formula booklet. Okay, right, let's move this into a place you can see it. So we've got acceleration due to gravity, g, 9.81. We've got permittivity of free space, epsilon naught, 8.85 times by 10 to the 12. And then we've got permeability. Okay, so we're looking for the permittivity one, which is epsilon naught. That's what we're looking for. So here's what I'm going to do. I'm going to write epsilon naught is equal to 8.85 times by 10 to the minus 12. Okay, I'm going to pop that away now because I don't need it anymore. Right. Believe we've got everything we need. So we just need to go about and substitute all these values in, rearrange, and then get R as a value. So first things first, force. Force is 8.2 times by 10 to the minus 8. 8.2 times by 10 to the minus 8 is equivalent to Q1. Q1 is 1.2 times by 10 to the minus 16 times by 1.7 times by 10 to the minus 16. All divided by 4 times by pi times by 8.85 times by 10 to the minus 12 times by r squared. I've only got one variable missing, but I need to rearrange this entire equation with this one variable. Here's what I'm going to do. I'm going to times both sides of the equation by r squared, therefore removing it from this divide and popping it up here. So it'll be 8.2 times by 10 to the minus 8 times by r squared equals the remainder of this. And what I'm also going to do is I'm going to divide both sides by 8.25 times by 10 to the minus 8, therefore removing it from this side and placing it down here in the place of the r squared. Okay, so what they're doing, in short, is they're doing a quick little swap. Alright, so we've got r squared equals 1.2 times by 10 to the minus 16 times by 1.7 times by 10 to the minus 16 all over 4 times by pi times by 8.85 times by 10 to the minus 12 times by 8.2 times by 10 to the minus 8. Right, I've got r squared, I only want r. I'm going to have to square root both sides. Now I've only got r. And this is the entire thing I need to chuck in my calculator. A lot of numbers here, I've got to make sure I do this correctly. Spend time on this. This question is worth 4 marks, but spend time making sure that you write this correctly into your calculator. So, square root, fraction, right, 1.2 times by, let's go times by 10 to the minus 16, times by 1.7 times by 10 to the minus 16. So far, so good. Okay, the top line is correct. I'm now moving down to the bottom line. Times by 4, times by shift pi, times by 8.85, times by 10 to the minus 12, times by 8.2, times by 10 to the minus 8. Right, everything should have been placed into the calculator correctly. I took my time on this, so I'm going to press the equal sign. We're going to get the answer of 4.72967 times by 10 to the minus 8 as a distance. R is therefore equal 4.73, rounding already, okay, times by 10 to the minus 8. And this is going to be a distance in meters. Everything is in SI units. Therefore, if everything else is in SI units, we must also do a distance in SI units. So as you can see, it's times by 10 to the minus 8 meters, which means this is very, very, very small. Okay, we're probably talking about nano here. Okay, so this would be about, what, maybe 47 or 417 nanometers. Very small distance. Okay, I need to get my conversions correct here. Either way, extremely small. Alright. Unfortunately with this, I'm not going to have to do any conversions. I'm just going to pop that answer straight in to the answer column, the answer line at the very bottom of the page. 4.73 times by 10 to the minus 8, and that is in meters. Another 4 marks, and I get to move on. Right. Ooh, this is an interesting question. Okay. Let's grab that formula booklet again. Right, let's quickly underline important information. 10 amps. A steady state direct current passes through the inductor coil that has 500 turns. 500 turns, that's important. Therefore, I'm probably going to need a formula that involves N and I, so that's going to be useful. The energy stored in the inductor coil, right, okay, that's going to be very useful as well. Energy formula. Calculate, right, okay, this changes everything. Calculate the induced back EMF voltage in the coil after the switch has been opened. So we're looking for the induced back EMF the second this turns off, and it's going to take 2 milliseconds as well. So there's going to be 2 formulas in this question, 7 marks total. Right. Probably useful to be on that page then. Perfect. Okay, first of all, energy stored in an inductor is this formula here, and we've got a fair amount of that information already. And then we're also going to need to use an induced EMF formula as well. And I'm probably going to go for this one. Yep, let's have a look at it. Right. W. This is for the energy stored in an inductor equation. W equals a half L I squared. Okay. Just popping that aside for a moment. Right. So, in terms of information that we have, W we've got as 37. We know what our half is, 0.5. We don't know what L is, and we've got I squared. I squared being the 10. Okay, so with that, I get to quickly rearrange this so that I'm solving for L. Divide by 0.5, so in other words times by 2, and then divide by 10 squared. Okay, so let's quickly rearrange this. 37.5. Let's just get rid of that. Let's write it again. 37.5 divided by 0.5 times by 10 squared equals L. Just get our calculator. 37.5 over 0.5 times by, I'm going to jump the gun, 10 squared is 100, so just writing 100, there we go, equals 0.75, equals 0.75. That's L. Okay. Right. I feel like I'm missing something. That formula isn't going to work immediately. I was going to jump straight to induced EMF. I got L, got R, got T. That wouldn't necessarily get me anywhere. Oh wait, no. Okay, right. Yeah, I'm going to go that way. I've just realised that there is two potential ways of going with this due to, I'm going to show you again this particular formula, induced EMF. I could go down this route, but if I go down this route, I would use number of turns, delta T, okay, a bit challenging. But this symbol, I have to solve for that symbol. However, I could use this, which I already solved. Okay, I've already solved for L, got it at 0.75. We've got I, delta I, the change in I. Now this is particularly odd because you shouldn't ever really have a change in your current. However, you would have a change in your current if you switch the thing off. Okay, so when it's on, obviously current will flow, but the second you switch it off, it's not going to flow, it's going to be 0. So you've got a change of 10 to 0, therefore the total change is going to be, well, 10. Okay, and then time, it says open for 2 milliseconds. Alright, so we've got a delta time as well, so we just need to rearrange those things, then we get to have our EMF. E, well, let's move this down a bit so we can see. E equals minus L di over dt. Okay, that's not looking too bad now. With that, I'm going to substitute some values in. We've got minus 0.75 times by di, changing I, well, going from 10, switching it off, it goes to 0, so 10 minus 0 is still 10. Over the change in time. The time is 2 milliseconds, that's not SI units, milliseconds to second. We need to divide this number by 1,000. So 2 times by 10 to the minus 3. And that's going to equal E, which is the equivalent of, let's grab a calculator. So 0.75 goes in front of the fraction, let's then put times, and let's go to the first one, which is 10. Bottom one is going to be 2 times by 10 to the minus 3. Press E equals 3,750. I forgot the minus symbol though, so what I'm going to do is I'm going to go back, I'm just going to put the minus there. There we go, minus 3750. EMF is in volts, so our answer is going to be minus 3,750 V. And that is that question done. We're going to move on. What I will do though quickly though is just show you back on this. This you definitely have to start with. You have to. No other way around it. You will be solving for this capital L. Okay, with this you could potentially use this equation because you've got L, you've got I, you've got N. You can then solve for this symbol here, and when you've got that symbol there, you can then use this formula here if you wanted to use a different way. But that's 3 formulas rather than the 2 formulas. This is safer using these 3 formulas if you don't quite understand how to use this delta I, delta T. Okay, because these are a lot simpler, okay, of an equation. All right. Okay, with that being said, I am going to move on now. And we're doing well for time. Unfortunately, we've got a bit of a tricky one to finish off with. A technician has measured waveforms of 2 sinusoidal AC supplies. Both waveforms have the same frequency. Right, we've got V1 as sine 2 sine of 2 theta, and we've got V2 as 3 sine 2 theta. So they're both in the same phase. As you can see, they're in the same phase because they basically sit on top of each other. They cross over this axis at the exact same point as well, so they are in phase with each other. We've been asked to, okay, well, this is already really easy. Calculate the form factor of the combined AC supplies V1 and V2. Anytime you have to do form factor, the answer is 1.11. So all I'm going to do is I'm going to chuck my answer in right now. All right. However, this will only get you 1 mark. We've got 8 marks to grab, so let's go back and actually do the working out. Show why that's the case in a moment. Okay, why it's 1.11. So we've got a peak value here of 2, and we've got a peak value here of 3. They've asked us to calculate the form factor of the combined AC supplies V1 V2. So first of all, we have to combine these. All right. They haven't asked us to draw out the equation or draw the line. We could go about drawing the line if we really wanted to. Okay, but essentially it will cross at this point here. It will still cross here. It will cross at -5 as well. Okay, it will cross here. It will cross back over here. So, you know, you could go about and actually just draw that very quickly and just show them that you understand it. All I'm going to do is I'm going to take the 2 peaks. 2 plus 3 equals 5. I'm going to just write a little sentence quickly. 5 volts equals peak voltage. I'm going to grab my formula booklet now. I'm going to look for the formula for single phase alternating current theory, which is this one. As you can see here, single phase alternating current theory. Everything I need is going to be in this part. Right. So the first thing I'm going to need to do is calculate the root mean squared. Root mean squared, okay, is the RMS voltage. As you can see just here, root mean squared, RMS voltage, and it is the peak voltage divided by the square root of 2 equals RMS voltage. Okay, the peak voltage I've just said was 5 volts. So 5 divided by the square root of 2 equals RMS. Let's write that down. 5 divided by square root of 2 equals RMS voltage, which I'm going to put in my calculator because I can't do it in my head, divided by square root of 2 equals 3.535533960. Let's just shorten that to 3.5355. That's RMS. Now that I've got that, okay, I need to get the waveform average value. In this case, the value we're on about is voltage. So average value equals 2 over pi times by the max value. Max value, we've already got. Okay. So, 5 times by 2 over pi equals average. Sorry, you can't see that. Let's change that. 5 times by 2 over pi equals average voltage. just going to show you which equation I'm looking at. Waveform average value, here we go. Okay, the reason why we're using value instead of voltage here is because you could also do this for current. Okay, but we don't care about current at the moment, we're only dealing with voltage, so waveform average value, so the average voltage equals 2 divided by pi times by the max value, which is the peak voltage that we had a moment ago, which is 5. So 5 times by 2 over pi. Okay, 5 times by 2 over pi equals average, which is equal to, right, let's work this out, 5 times by 2 over pi. 3.1, okay, 3.183098. Right, I'm nearly there. Last formula. We've been asked to calculate the form factor. We can now look at the form factor, which is at the bottom here. Form factor equals the RMS value over the average value. As you can see here, I've got the RMS value over the average value. I'm just going to take these two numbers. Oh, sorry. You can't see. Now you can see. I've got the RMS value over the average value. I'm going to plug those into a calculator, and then I'm going to get my answer of 1.11. So, 3.5355 over 3.183 equals 1.11, oh sorry you can't see that, 1.1107, Okay, you could put the exact values in there if you want. You're going to still get value of 1.1107. I can't tell for the rest, unfortunately. I don't remember that far, however, these first 5 digits. Either way, though, you only need the first 3. The examiners only expect you to have the first 3, the 1.11. Okay, hence why my value at the beginning was 1.11. You may be thinking, how did he know straight away? It comes back down to the formulas. Okay, I'll quickly write this out. It says RMS divided by the average value. So what I'm going to do is I'm going to write the formula for RMS next to the formula for average value. Okay, and then we could see what we're dealing with. RMS was peak V divided by root 2. And it was divided by, because we're taking the RMS divided by the average, so the average formula now was 2 times by peak divided by pi. That was the formula, okay, for the form factor. Form factor was RMS divided by average value, and these are the two formulas for each of those. If we do our basic maths with keep, change, flip, you will see that it's peak voltage over root 2, so that was keep, change the divide to times, flip this equals pi over 2 peak. Right. Now what you can do is, if you've got any like terms on diagonals, you can eliminate them. I've got peak V and I've got peak V. They're on diagonal terms, therefore I can eliminate them. This then becomes a formula of 1 over root 2 times by pi over 2. If you plug that into your calculator, you'll get a value of 1.1107, so on and so forth. Okay, hence why the second I saw the form factor, I immediately knew it was 1.11. Okay. In other words, this question here is just a proof question. All right, you should know the value going into your exam. Right, that's it for this paper. Okay, section C is now finished. I'll catch you in the next video.